All right, so here's our limit, our tangent line slope, and it's basically the same formula, right? Our formulas, except we just add the limit. So we're saying, hey, instead of just taking these 2 points, x and a, what if I just get closer and closer to a, right? And really this is a two-sided limit, so from either side, what if I just keep getting values that are where x is closer and closer to a, right? Then what will the value be? And so as you can see, and as we've explored before, we go from our slope of the secant line to being, fairly accurate to the speed at that particular point, or the slope at that particular point, but getting more and more accurate as we get closer and closer to a, right? To the point where we're actually just finding the value or the slope at that particular point, and it's not even a secant line anymore, but rather the slope of a tangent line. Okay. Same thing here. What we're saying is we're getting that distance between a and some other point, right? This distance here, we're getting that to be super, super small to the point where we're approaching zero, right? And so that's what these definitions give us. These formulas give us. Okay, and so we can see that we're actually finding the slope of this tangent line rather than the slope of a secant line. All right, and we're finding instantaneous rate of change rather than average rate of change. Okay, so basically we started with our secant formulas, right? Our difference quotient here and our increment formula here, and then we just introduced the limit. We put the limit in front of both of those, right? To where we have, hey, what if these get super close together, right? What if this value gets as close as possible to this value, all right? And the same thing here, except for when those values get super close, if we use this representation, then we're saying that, hey, this denominator is getting super, super close to zero, right? This output is getting super, super close to this output. All right, so that's this is the definition of the slope of a tangent line using limits and our difference quotient. All right, so let's take a look at both formulas, and you can see that either way we'll get the same result. So let's start by using the difference quotient. Okay, let's start by saying, okay, M10 equals the limit as x approaches a of f of x minus f of a all over x minus a. Okay, so let's start with that equation. So here we have f of x equals x squared, and our a value is x equals 3, right? We want to find the tangent line at 3. Okay, so this is the slope of the tangent line at x equals a, right? Is what this formula tells us. Okay, so in this case, a is 3, and so we're going to say, okay, well, M10, or the slope of the tangent line, is the limit as x approaches 3 of f of 3, or excuse me, f of x minus f of 3 all over x minus 3. Okay, so now we know we can't just plug in 3 because we're going to get 0 in the denominator, right? So we actually have to evaluate this either algebraically, we could use a table, the graph, etc. So first of all, I know f of x equals x squared, so I'm just going to put x squared in here, right? And then f of 3 is 3 squared, right, which is 9. So I'm just going to put 9 in right here. All right, and so what I'll end up getting is I'll carry down the limit. So it'll be the limit as x approaches 3. And instead of f of x, I'm going to put x squared minus, instead of f of 3, I'm going to put 9. And then we have x minus 3 here on the bottom. Now, here we have a rational expression, right? So if we can, we want to try to factor on top and bottom, right, to do this algebraically. And so I can't factor the denominator because it's just, it's not a difference of 2 squares. It's not a difference of cubes or anything like that. There's no common factor. That's as far as we can go. But x squared minus 9, I can factor that, right? I can turn that into x plus 3, x minus 3, right? It's the difference of two squares. So I just take the square root of this, put it here and here, and the square root of this goes here and here, right? And then you just change the signs, plus and a minus there. So I'm going to bring down the limit and bring down the denominator. And now we can see that these are the same. So essentially we can just cancel those out. We know there's going to be a removable discontinuity there, but as far as evaluating the limit, now it turns into just a direct evaluation where I can just input 3 here for x, so it'll be 3 plus 3, which is 6. Okay, so we just found that the slope of the tangent line at 3, at x equals 3, is 6. Okay. All right. So that's also the instantaneous velocity at that point, right? The instantaneous rate of change at that particular point. Okay. So that's using that formula. Let's real quickly, let me show you the other formula.